All right, class, I hope you liked the last video about covalent bonding. Now I want to talk a little bit about spell that right. Ionic, that's C, bonding, an ionic bond. Things that are ionically bonded we refer to usually generically as a salt. The common classic one that we think about here is sodium chloride. Sodium chloride, common table salt. All right, so sodium chloride, sodium has 11 protons, chlorine has 17 protons. So these are going to be pretty big atoms that we draw, so we better get to it. So I'll draw the sodium over here with its 11 protons. I'm going to be drawing for a little while, so bear with me. It's coming along pretty well. And this lone single electron out on the outer valence shell. Get out of the way so you can see it. Sodium. Chlorine has 17 protons. Likewise, it's going to give me a minute to draw this. Okay, and what do I mean? 7 more. 1, 2, 3, 4, 5, 6, 7. Nice big chlorine atom here. This atom over here, this side, the chlorine, is very, spelt that wrong, electronegative. We were just talking about electronegativity. The sodium over here is not very electronegative. Over here, we almost say it's almost electropositive, and I'll talk a little bit about that and what we mean by that here in a second. So if you remember what we talk about oftentimes when we talk about stability and whether a molecule is stable, that usually means the outer valence shell is full. That's one of the indicators of stability, that we can sort of look at something and say, is this stable, or is this going to go out and keep reacting with stuff? If we look at how the valence shells are and whether or not they're full or close to being full or whatever, we can do that commonly, right? So here's an outer shell that can hold 8 electrons-ish. It has one. All right, so this is nowhere close to being full. It's like if it wasn't for this one electron, that shell would be empty. Chlorine over here, it's 1 short. It has 7 valence electrons. It's most stable at 8 on that shell. So it's like if the sodium could just get rid of 1, its shell would be full because the second one would be the outer one. If the chlorine could add 1, then its shell would be full and it would be super stable. And so these two elements sort of come into this mutually energetically agreeable agreement, which is, if I just take that electron and move it over here, now it has 17 proteins and 18 electrons. It now has the charge of -1 because it has an extra electron. We would call this an anion. Over here, we can now just, this shell just kind of goes away. Try to erase it as best I can. It's like that. The shell goes away because its electron has moved over. So now it has 11 protons and 10 electrons. It has a charge of +1. We would call that a cation. And so now we just have basic, simple electrostatic attraction. Here's something with a +1 charge. Here's something with a -1 charge. They attract to each other just from the static electrical charge of having opposite, poles, acting like opposite poles, a positive and a negative. This bond that forms, it's not a sharing, it's just an electrostatic attraction. That is an ionic bond, a bond between 2 ions from either the removal or the gaining of electrons over and above or under the number of protons in the nucleus. So that is how I would draw an ionic bond for something like a homework assignment. So I hope that was helpful. I hope that was clear. Please let me know if you have any questions about it, if there's anything you'd like me to draw a little more clearly. And I really appreciate it. So anytime you have any combination that you're going to draw as an ionic bond, like for a homework assignment, for example, go ahead and sketch them out, right? And seeing how the loss or gain of electrons might provide electrostatic basis for attraction, and that would be the ionic bond. And it's almost always between the first two columns in the periodic table and the second to the last, the chlorine-fluorine column over here. So that's where the differences in electronegativity are great enough that they can actually do the stealing of the electron instead of just the borrowing. So covalent bond, nonpolar, equal sharing of electrons; polar, unequal sharing of electrons; an ionic bond, fully taking the electron and then having electrostatic attraction. So that's sort of the relationship there. Sometimes I say that an ionic bond is the extreme case of a polar covalent bond, where the more electronegative one is actually pulling so hard on the electron that it actually takes it and onto itself 100% of the time, and electrostatic attraction then takes it over. So thanks so much. Let me know if you have any questions, and I'll see you guys soon.